Okay, well now let's take a look here at 5.3.3. We're going to be looking here today at another new test. And this one's going to be really nice because it's going to build off of the test that we covered last time, the integral test. And I kind of have it summarized right here. I'm going to go ahead and take a look back at the list again that we happen to be forming, because again, we're going to be adding something in here. We're going to be adding in, a special kind of new series. So far we had 3 series types, and now we're going to introduce a new one. This one is going to be a p-series. A p-series is a series that always has the same general shape as follows. This is the series with a formula of 1 over n to some power, n starting at 1 and going up to forever. Okay, so notice here that in a p-series, I'm going to have, again, my counter variable is dealing with the base of this number to a power combo that's here. P is just going to stand for any number. So this could be something like 1 over n squared, 1 over n to the pi, 1 over n to the 16 thirds. I could have any sort of number up there, but n is still just that counter variable. Okay, we're going to see that there's ultimately kind of an interesting way to link together the ideas of a p-series and the integral test that we talked about last time. So let's take a look at what we have here. Last time we said that with the integral test, we would suppose that if a function that we had that matched up with our sequence was continuous, positive, and decreasing on the given interval, then whatever the improper integral did, the series also did. So we're going to try to go ahead and use that fact to help here with a series of a p-series. Use the integral test to show that the following series is convergent when the constant p, when the number that I pick for p actually is greater than 1. Okay, so I'm going to go ahead and attempt to try to work with this. This, again, shouldn't be too terribly difficult because I'm going to try to use the integral test up above. So first I'm going to think about my matching function. So I'm going to say, how about we let f of x be equal to 1 over x to the p? Again, p is just a mystery number. Well, automatically I could start to see that if I want to use the integral test, I better check all the conditions. This function here is clearly continuous on 1 to forever because the only thing that makes it undefined is 0. So f of x is continuous. I also can see that it's definitely going to be positive. And since I have number over something that's clearly going to only be getting larger, we said that last time we can just automatically assert that it is decreasing. And all of this is true on the interval from 1 to infinity. Notice all this is true regardless of the value of p. Okay, so now I can go ahead and calculate the integral from 1 to infinity of 1 over x to the p. Now, again, I can easily start to convert this to a limit. And I just need to go ahead and think about an antiderivative. Now, the antiderivative here is a little bit messy looking. It's not too bad. Keep in mind that I could rewrite the current function as x to the power negative p if I wanted to help me think through the antiderivative. And so if I had something like x to the negative third, I could think about how I would do the antiderivative of something like that. I would typically add 1 back to that power and then divide by that new power. So like here I would do -2 as the exponent and then 1 over -2 in the front. Well, I should do the exact same thing then when I come across what I have here. I should end up with x to the negative p plus 1 over negative p plus 1. And I'm just going to write that all as one fraction to save on space. Okay. Of course, I need to evaluate that from 1 to t. Remember, those are values that are going in place of x. So if I rewrite this again, this is going to look like, I'm going to have t. I'm going to rewrite this really quickly as 1 minus p as the power and 1 minus p in the denominator. Notice what I'm subtracting over here, though, is pretty obviously 1 over 1 minus p. So what I can see is that only one of these terms in here actually has the variable of t, so only one of these is going to get moved by the limit. This other piece over here is just a constant, so that's going to hang around. So really whatever this first term does is going to dictate everything. If this term converges, then the whole thing converges. And if this diverges, the whole thing diverges. Here's where it becomes really important to consider what's happening with the value of p. If p is a number that's bigger than 1, take a moment to think about what we can say about this exponent that's occurring up here. We should be able to argue that that exponent is going to be negative. And if that exponent is negative, I could choose to rewrite this t to a negative power in the denominator. But if t then occurs in the denominator, it's going to make this entire fraction go to 0, and so I will end up with 0 minus 1 over 1 minus p. I'll get negative 1 over 1 minus p. This, of course, means that our integral is convergent, and therefore by the integral test, the series 1 over n to the p converges. Okay, so we kind of found that in a p series, if the value of p is bigger than the number 1, automatically I have a convergent series. Okay, we're going to go ahead down here and take a look at another part. What would happen if I changed where the value of p goes? Now, here's the best part. Since I'm still working with the exact same function, and I still know, oops, up here, this seems to have been not fully written. I still know that that function is continuous, positive, and decreasing. And I pretty much can get all the way through the exact same portion of the limit calculation. So really quickly, I'm just going to go ahead and rejot all of that information down. Notice here I'm going to skip through this limit calculation slightly. So I can think about what happens. Now I have to think about, again, what's going to be true of that exponent. Keep in mind here, p is going to be a value from 0 to 1. If that's the case, what could you tell me about the exponent? Well, it would have to be positive, right? It's got to be a positive exponent, which means I don't need to move t to the denominator. If t is going to stay in the numerator, though, and t heads towards infinity, I can see that this is going to turn into infinity minus 1 over 1 minus p, which is going to become infinitely large. So in this case, 1 over x to the p, that improper integral is divergent. And so our series is divergent. Okay. So this is great. We can start to almost kind of completely classify, based on what the value of p is, what this series will do, this p series. Okay. Now, one final thing before we end this segment of the video. We also might want to consider some of the other values of p that we haven't yet talked about. If you take a look at the two different values of p that we've worked with thus far, we've worked with p's that are bigger than 1 and p's that are between 0 and 1. But there are certainly other numbers that p could be. You can start to think about what some of those other values might be. One value you might notice is that p could be the number 1. If P was the number 1, can you think about what this series that we have would actually look like if P was a 1? If P is a 1, you can probably see that, yes, you get the harmonic series. And we know the harmonic series diverges. So we can kind of tack on to this group down here that if it's equal to 1, we still get divergent. We could also, though, see that there are negative values of P that are possible, right? And 0 might be possible. So what happens if I use 0? Let's start with that value. Notice if I plug in the value of 0 for P, that's going to be number to the power 0. Well, that's just going to be 1 over 1. And when I think about the addition problem, 1 over 1 plus 1 over 1 plus 1 over 1, so on and so forth, that's just adding up ones for the rest of time. And there's no way that converges. That's pretty easy to see. I could do the exact same thing when I take a look at something with a negative power. If I have n to a negative power, that's going to allow me to rewrite this as n to the power p. And I'm going to have some big problems there because again, I can easily test those series with a test for divergence. And I'd ask you to try to take a look at that on your own to make sure that you agree. Okay. Last thing before we go ahead and work through some of the examples is we'll write down here what we call then our p-series test. So we'll say that the p-series 1 over n to the p, n starts at 1 and goes to infinity, is convergent if if p is greater than 1, and it is divergent if p is any other value. Okay. So we have a complete classification for this type of series. We know exactly what it does. It is all based on the p. We'll take a look at the examples in the next video.